The prototype sits on the bench in the Izhevsk machine-building plant, early 1969. The workshop smells of machine oil and welding flux. Kalashnikov walks past lathes and stamping presses to reach the table where the PKM has been partially disassembled. The barrel lies separate from the receiver. The bolt carrier, still warm from test firing, rests next to a coil of non-disintegrating belt. Each link in the belt holds a 7.62 54 mm cartridge, the brass cases reflecting the overhead fluorescent lights. An engineer named Sergei marks measurements in a notebook. He has been testing the feed mechanism's timing for 3 days. The belt moves through the gun smoothly, but there's a question about the camtrack's angle, where it engages the feed lever. If the angle is too steep, the mechanism binds under continuous operation. If it's too shallow, the belt doesn't advance reliably. Kalashnikov picks up the bolt carrier, examining the cam surface. His hands know this shape intimately. It's fundamentally the same rotating bolt he designed for the AK-47 in 1947, but scaled for different forces. The challenge is visible in the hardware's construction. The receiver is stamped sheet metal, bent and riveted, rather than machined from solid steel. This makes it lighter, but introduces flex that doesn't exist in milled receivers. The barrel lacks chrome lining, reducing weight by nearly 1 kilogram, but accelerating erosion from hot gases. The stock is wood, not synthetic, because polymer molding facilities aren't available at the required scale. Every choice reflects a constraint, and every constraint reflects the reality of Soviet manufacturing capacity in 1969. Kalashnikov opens a drawer and removes a PK machine gun, the PKM's predecessor from 1961. He sets both units side by side. The PK is heavier, its receiver milled from solid steel. Its barrel is chrome-lined, but it weighs over 9 kilograms, and field units have reported that carrying it over long distances causes fatigue that affects operational effectiveness. The directive from the military was clear: reduce weight to 7.5 kilograms maximum while maintaining reliability in Arctic and desert conditions. Sergei points to the belt feed mechanism. The timing works consistently now, he says. We modified the feed powel geometry yesterday. The belt advances 3 millimeters earlier in the cycle, which gives the next round more time to align before the bolt strips it from the link. Kalashnikov nods. He lifts the PKM's receiver, feeling its weight distribution. The center of mass is slightly forward of the pistol grip, which means the operator's supporting hand will bear most of the load during movement. This is intentional. Weight in the barrel area provides stability during firing, while keeping the rear light reduces fatigue. The workshop door opens. A quality inspector enters with documents requiring signature. The PKM has passed durability testing at -40 degrees Celsius, but there are questions about barrel life expectancy. Without chrome lining, the rifling degrades faster under sustained use. Kalashnikov's response is engineering logic. If the barrel can be changed in 15 seconds, barrel longevity becomes less critical than reliability and weight. The quick-change barrel system compensates for material constraints. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. Kalashnikov sits at his desk in the Design Bureau, January 1969. A technical drawing is spread before him, showing the PKM's feed mechanism in cross-section. He sketches modifications to the cam track with a mechanical pencil, erasing and redrawing the same curve 5 times. The angle must allow the feed lever to pull the belt forward precisely as the bolt unlocks from the barrel, creating a window of time where the cartridge can be extracted from the link without binding. The pressure comes from multiple directions simultaneously. The Soviet military needs the PKM in production by the end of the year. Warsaw Pact allies have requested specifications for domestic manufacturing, and there's an unspoken competition with Western designs, particularly the American M60, which uses a different operating system entirely. The M60 relies on a gas-operated rotating bolt design borrowed from the German MG42, but it's mechanically complex and difficult to maintain. Kalashnikov's advantage is simplicity, but simplicity only matters if the equipment actually works under field conditions. A colleague named Victor enters with test results from the previous week's trials. The PKM has completed a 10,000-round endurance test without mechanical failure, but barrel temperature reached levels that caused the wooden stock to char slightly where it meets the receiver. This is a solvable problem. A heat shield can be added between the barrel and stock, but it reveals how little margin exists in the design. The device operates at the edge of its material's capabilities because staying within those limits would make it too heavy. Kalashnikov reviews the numbers. The PK, with its milled receiver and chrome-lined barrel, weighs 9 kilograms. The PKM, with stamped construction and unlined barrel, weighs 7.5 kilograms. That 5-kilogram difference means a unit can carry more ammunition or reduce each person's load proportionally. Over a 20-kilometer march, the difference becomes meaningful. Over a campaign lasting months, it becomes decisive. But weight reduction introduces problems. Stamped receivers flex under stress, which can affect headspace, the critical distance between the bolt face and the cartridge case head. If headspace varies during operation, cartridge cases can rupture, venting hot gases into the receiver. Kalashnikov addresses this by designing the barrel to lock rigidly into the receiver through a trunnion system, creating a stable platform for the bolt to cycle against. The rest of the receiver can flex slightly without affecting function. The feed mechanism is the most delicate part of the entire system. A belt-fed system has to manage 3 simultaneous operations: extract the fired case, chamber the next round, and advance the belt. The timing has to be precise across hundreds of cycles per minute. Too early, and the belt jams. Too late, and the bolt tries to chamber a round that hasn't been positioned yet. Kalashnikov's solution uses the bolt carrier's reciprocating motion to drive a cam that pulls the belt forward through a feed pole. The pole is spring-loaded, so if resistance increases, the mechanism can slip rather than break. Victor points to a note in the test report. Barrel change time averaged 12 seconds across 10 trials. This is faster than the M60, which requires tools and careful alignment. The PKM's barrel has a carrying handle that also serves as the locking mechanism. The operator pulls the handle up, which rotates a collar that releases the barrel from the receiver. Slide the old barrel out, slide the new one in, push the handle down. The system is designed to be operated while wearing heavy gloves in sub-zero temperatures. Kalashnikov makes another sketch, this time showing the bolt head locking lugs. They're identical in geometry to the AK-47's lugs, which means manufacturing facilities don't need retooling. The bolt head rotates 90 degrees to lock, camming into recesses cut into the barrel extension. The same geometry, the same movement, but scaled to handle sustained use rather than semi-automatic operation. The mechanism begins with the trigger pull. A sear releases the bolt carrier, which is driven forward by a return spring compressed during the previous cycle. As the bolt carrier moves forward, the bolt head strips a cartridge from the belt, pulling it free from the metal link that holds it. This happens because the bolt face has an extractor claw that grips the cartridge rim, and forward momentum carries the cartridge into the chamber. At the same moment, the bolt is rotating. A cam track cut into the bolt carrier forces the bolt head to turn 90 degrees as it moves forward. This rotation aligns 2 locking lugs on the bolt head with 2 recesses in the barrel extension. When the bolt reaches the forward position, the lugs seat completely, locking the bolt to the barrel. The chamber is now sealed. The firing pin, which sits inside the bolt carrier, strikes the cartridge primer. The powder ignites. Pressure builds rapidly. The projectile accelerates down the barrel while gas pressure pushes backward against the bolt face with tremendous force. But the bolt cannot move because the locking lugs prevent rotation, and rotation is required for the bolt to unlock. The barrel itself absorbs the initial energy, compressing against the receiver. Then a small port drilled in the barrel allows high-pressure gas to enter a tube that runs back to the gas block above the barrel. This gas strikes a piston connected to the bolt carrier. The piston is driven backward, pulling the bolt carrier with it. As the bolt carrier moves backward, the cam track reverses its action, rotating the bolt head 90 degrees in the opposite direction. The locking lugs disengage from the barrel extension. The bolt unlocks. Momentum carries the bolt carrier backward, and the extractor claw pulls the spent cartridge case from the chamber. An ejector pin strikes the case, throwing it clear of the receiver. While this is happening, the belt feed mechanism activates. The bolt carrier's rearward motion drives a cam that engages the feed lever. The feed lever is connected to a feed pawl, which grips the belt and pulls it forward. Each link in the belt moves exactly one position, positioning the next cartridge for the bolt to strip on the forward stroke. The timing is precise. The belt must advance while the bolt is fully rearward, creating space for the cartridge to move without interference. The return spring, now compressed by the bolt carrier's rearward travel, begins pushing the system forward again. The cycle repeats. At 650 rounds per minute, the entire sequence occurs more than 10 times per second. Each component, bolt, carrier, piston, cam, feed lever, pawl, spring, must complete its motion in the exact sequence, or the device stops functioning. What makes this remarkable is that the PKM uses essentially the same bolt design as the AK-47, a rifle that operates semi-automatically or in short bursts. The bolt head is the same size, the locking lugs are the same shape, and the camming angle is nearly identical. But the PKM fires continuously, generating heat and force that would destroy a standard rifle bolt in seconds. Kalashnikov solved this not by changing the bolt, but by changing everything around it. The heavier bolt carrier spreads forces over a longer distance. The stronger return spring controls the timing. The gas system is adjustable, allowing the operator to increase or decrease gas pressure based on conditions. The feed mechanism itself is the visible difference. Where the AK-47 uses a magazine that simply holds cartridges in position, the PKM must actively pull the belt through the receiver, extract each cartridge, and push the belt out the other side. The non-disintegrating belt means every link must travel the full length of the receiver, entering on the left side and exiting on the right. This requires a feed tray, a cover that guides the belt, and precise spacing to prevent links from overlapping or jamming. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The test range outside Izhevsk, February 1969. Snow covers the ground, and the temperature hovers at -25 degrees Celsius. A PKM prototype is mounted on a tripod, its barrel pointed at a series of targets positioned at various distances. Kalashnikov stands behind the line with 2 engineers and a military observer from the main artillery directorate. The observer holds a clipboard, recording data for the official evaluation report. The test begins with a cold start. The equipment has been sitting in an unheated shed overnight, meaning all the metal components are at ambient temperature. The operator loads a belt, primes the weapon, and begins firing. The first burst is 20 rounds. The mechanism cycles smoothly, ejecting spent cases into a pile on the frozen ground. The military observer notes function normal at -25 degrees, cold start. Next, a sustained fire test. The operator fires 200 rounds continuously without pause. Smoke rises from the barrel as the metal heats rapidly. The wooden stock begins to smell of scorched wood where it's closest to the barrel. After 200 rounds, the operator stops and immediately attempts a barrel change. He pulls the carrying handle upward, rotating the barrel lock. The hot barrel slides out and a cold replacement barrel is inserted. The observer clicks a stopwatch. 14 seconds. Acceptable. But there's a problem. When the operator resumes firing with the fresh barrel, the rate of fire has decreased noticeably. Kalashnikov observes the ejected cases. They're landing closer to the gun than before, indicating reduced bolt velocity. He walks to the device and adjusts the gas regulator, a small knob on the gas block. This changes how much gas pressure reaches the piston. With more gas, the bolt carrier gains more energy, restoring the normal cyclic rate. The observer makes a note. Gas system requires adjustment after sustained fire due to residue buildup. The next test involves deliberate stress. The operator pours sand into the receiver while the device is firing. The mechanism continues cycling, though the ejection pattern becomes erratic. Some spent cases fail to clear the ejection port completely, falling back into the receiver. After 50 rounds, the gun stops. Kalashnikov and the engineers disassemble it on the spot. Sand has accumulated in the feed mechanism, binding the feed pole. They clean it with a rag and compressed air, reassemble the hardware, and resume firing. The observer writes, "Feed mechanism vulnerable to particulate contamination, but recoverable with field cleaning." A different prototype is brought out, this one with a modified feed pole geometry. The spring tension has been increased, and the pole itself is slightly shorter. The same sand test is repeated. This time, the device fires 150 rounds before stopping, a significant improvement. The modification works because the stronger spring forces the pole to snap back more aggressively, reducing the time that sand can accumulate in the mechanism. The final test is endurance. The PKM fires 5,000 rounds over the course of 3 hours, with barrel changes every 500 rounds. By round 3,000, the receiver has become noticeably hot to the touch, even through gloves. By round 4,500, the return spring's tension has weakened slightly due to heat fatigue, causing the cyclic rate to drop from 650 to approximately 600 rounds per minute. At 5,000 rounds, the operator stops, and the hardware is immediately disassembled for inspection. The barrel shows rifling erosion, as expected without chrome lining. The bolt face has minor pitting from repeated primer strikes. The extractor claw shows wear, but remains functional. The feed pole has a small crack forming at the base, where stress concentrates during belt advancement. Kalashnikov examines the crack under a magnifying glass. This is useful information. The pole can be redesigned with a radius fillet to distribute stress more evenly. The military observer completes his report. The PKM has demonstrated acceptable reliability across temperature extremes, resistance to contamination within limits, and maintainability under field conditions. The recommendation is to proceed with manufacturing, pending minor modifications to the feed pole and gas regulator. Kalashnikov signs the document, acknowledging that the design is not perfect, but is sufficient for the requirements. Back in the workshop, Kalashnikov disassembles the test weapon completely. Each component is laid out in sequence: receiver, bolt carrier, bolt head, firing pin, return spring, gas piston, feed mechanism, barrel. He picks up the bolt head, the same component that exists in millions of AK-47 rifles across the Soviet Union and Allied nations. It weighs 113 grams. The locking lugs are 8 millimeters wide and cut to a depth that provides 12 square millimeters of bearing surface against the barrel extension. This is the final curiosity. How does a bolt designed for a semi-automatic rifle survive in a machine gun operating continuously at 650 rounds per minute? The forces involved are dramatically different. An AK-47 bolt might experience peak pressures of 3,000 atmospheres for a fraction of a second, then rest while the user reacquires the target. A machine gun bolt experiences the same peak pressure 10 times per second for minutes at a time, generating cumulative heat and mechanical stress that would crack or deform a weaker design. Kalashnikov's solution was to manage energy through geometry and timing, not mass. The bolt head itself is unchanged, but the bolt carrier is significantly heavier and longer. When gas pressure drives the piston backward, the force is applied to the bolt carrier first. The carrier has greater mass and travels a greater distance, absorbing energy over time and space rather than instantaneously. By the time the carrier's rearward motion begins rotating the bolt to unlock it, the projectile has already left the barrel and chamber pressure has dropped to safe levels. The return spring is where the design becomes mathematically precise. A spring stores energy proportional to its compression distance. The PKM's return spring is 320 millimeters long and compresses 80 millimeters during each cycle. This compression absorbs the bolt carrier's kinetic energy, converting motion into potential energy stored in the spring. When the spring releases, it converts that potential energy back into motion, driving the bolt carrier forward again. The spring rate, the force required to compress it 1 millimeter, is calibrated to produce exactly the right cyclic rate for the weapon's intended purpose. But springs fatigue. High-temperature operation accelerates this fatigue. After the 5,000-round test, the return spring had lost approximately 8% of its original tension. This is acceptable for a component designed to be field replaceable. A user carries spare barrels. Carrying a spare return spring adds negligible weight. The design anticipates component wear and provides simple replacement procedures. The bolt's rotary locking system has another advantage. It's self-cleaning to a degree. Each rotation of the bolt head wipes debris from the locking recesses in the barrel extension. Residue and carbon buildup are mechanically scraped away by the bolt lugs during the lock-unlock cycle. This is less effective than chrome plating would be, but it's sufficient when combined with regular maintenance. The design uses motion to solve a material problem. Kalashnikov sketches calculations in his notebook. The bolt unlocks when chamber pressure has dropped to approximately 500 atmospheres, safe for extraction, but still high enough that residual gas pressure helps drive the empty case rearward. If the bolt unlocked earlier, case ruptures would occur. If it unlocked later, the mechanism would lose efficiency, requiring a heavier spring and increasing felt recoil. The timing is determined by the cam track angle and the piston's travel distance, both of which can be adjusted during manufacturing. The feed mechanism's timing is equally critical. The belt must advance while the bolt is fully rearward, but not so early that the advancing cartridge interferes with the ejecting case. The cam that drives the feed lever is positioned on the bolt carrier, so that it engages the lever only after the carrier has traveled backward far enough to clear the ejection port. This happens automatically, mechanically, without sensors or electronics. The geometry enforces the sequence. What emerges from this analysis is a picture of engineering constrained by reality. Kalashnikov could not use exotic materials, complex electronics or precision manufacturing beyond Soviet industrial capacity. He worked with stamped steel, wood, and spring wire. The genius is in arranging these ordinary materials into a system that functions reliably under extraordinary conditions. The bolt is not stronger than the AK-47's bolt. It simply operates within a system designed to protect it from forces it cannot withstand alone. The PKM entered full production in late 1969 and remained in continuous manufacture for more than 3 decades. By the time production slowed in the early 2000s, hundreds of thousands of examples existed across dozens of countries. The weapon appears in inventories from Cuba to Vietnam, from Poland to Syria. This proliferation happened not through aggressive marketing, but through simple effectiveness. Forces adopted the PKM because it worked in climates and conditions where other systems failed. The design influenced subsequent hardware development in ways both obvious and subtle. The stamped receiver construction became standard for Soviet small arms, reducing manufacturing costs and enabling production scaling. The quick-change barrel system was copied by multiple nations seeking to modernize their own equipment. Even the non-disintegrating belt, initially seen as a limitation, proved advantageous in contexts where resupply was uncertain and reusable belts could be loaded repeatedly from loose cartridges. But the PKM's legacy is not primarily about the device itself. It's about a philosophy of engineering that prioritized function over perfection. Kalashnikov designed for the world as it existed, not as theorists imagined it should be. He accepted that barrels would wear out and made them easy to replace. He accepted that maintenance would be performed by minimally trained personnel and made the hardware simple to disassemble. He accepted that manufacturing would occur in facilities with limited precision and designed components that tolerated variation. This approach stands in contrast to much of Western development during the same period, which often pursued theoretical superiority at the cost of practical reliability. The M60 machine gun, for example, used a more advanced operating system but required more careful maintenance and suffered from parts breakage under sustained use. The M60's barrel change procedure required specialized gloves and careful timing to avoid injury. The PKM's barrel could be changed bare-handed if necessary, with only minor discomfort. The engineering lesson embedded in the PKM is that constraints are not obstacles to overcome, but realities to work within. Soviet factories could not produce chrome-lined barrels at the required scale, so Kalashnikov designed a barrel that didn't need chrome lining. Soviet metallurgy could not consistently produce receivers with tight tolerances, so he designed a system where slight variations in receiver dimensions did not affect function. Every limitation became an input to the design process rather than an excuse for failure. In retrospect, the PKM represents a specific moment in industrial history. It was designed for mass mobilization scenarios, where many units would need to be equipped rapidly from existing stockpiles and industrial capacity. This scenario never materialized in the way planners anticipated, but the systems designed for that scenario proved adaptable to conflicts that actually occurred: irregular engagements, expeditionary operations, and asymmetric situations. The PKM's simplicity, which was engineered for conscript forces, made it suitable for irregular groups with minimal logistical support. Kalashnikov himself rarely spoke about the PKM in later years, focusing more attention on the AK-47's cultural impact. But engineers who worked with him remember the PKM as perhaps his most refined design, the product of 2 decades of experience applied to a constrained problem. Where the AK-47 was revolutionary, the PKM was evolutionary, taking proven concepts and adapting them to new requirements without unnecessary innovation. The hardware still appears in various regions today, more than 50 years after its introduction. Barrels have been replaced countless times, receivers show wear from decades of use. But the fundamental system continues functioning because it was designed to function in exactly these conditions: aged, worn, maintained sporadically, operated by users who may not fully understand its mechanism. The engineering holds because it was never dependent on perfect conditions. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching. Would you like me to generate a technical diagram showing the PKM's gas-operated bolt carrier and cam mechanism?